next we're going to be considering the following language. So let's consider, we're going to call it ls. So ls is going to be the language for which we consider binary strings that have this form. 0 to the I, 1 to the j, such that, I'll make this a 1 just to make that a little easier to parse, where the number of zeros is greater than the number of ones. Or simply, I is strictly bigger than j. So we're going to be proving, that ls is not regular. So we're going to use contradiction to do this. So the first thing we have to do is make sure we clear what we're doing. So if I want to show that it is not regular using contradiction, I have to assume that it is, right? That it is regular. So assume ls is regular. So let's assume that. So what's a property that all regular languages have? The pumping lemma, right? So why don't we use that to help us go about this? Remember, the pumping lemma gives us the pumping length. It is a constant that we can play around with, but I don't know what it is. Remember, just like the conversation I had with my dinosaur friend here. If I say, hey, look, my language is regular, the dinosaur is going to give me p. I don't know what p is until I get it. So my argument has to work regardless of what p is. So then from the pumping lemma, let's say by the pumping lemma, let's go from the pumping lemma. I'm going to abbreviate that as just PL. There is a constant P that satisfies its conditions, namely the ones for the pumping lemma. That satisfies its conditions. So just as a tip, if you're not sure what I mean by this, its conditions, I'm referring to the conditions of the pumping lemma. Satisfies its conditions. So the big thing that we have to do is select that string W. Remember, it has to be in the language, has to be an ls, and has to have length at least the pumping length, P. So we got to think carefully about how we pick this string. Now, often in problems like this, where you want to make sure that the number of zeros is greater than the number of ones, it's usually a good idea to try to make one that looks kind of like that, but make it so that you could fudge around with it in a way that you know what's going to happen with the part that you can pump. So here's a suggestion for how I would go about this. So I'm going to try selecting W to be 0 to the P plus 1, 1 to the P. Notice that the length is indeed at least P, but also notice that by putting at least P of the symbols in the zeros part, akin to one of our previous examples, I can guarantee what? So if I look at any way I split the string, so if I have a whole bunch of zeros, then I have a bunch of ones, I know that there's P plus 1 many of these, and there's P many of those. The pumping lemma says that at least there's going to be something going on over here. So remember that no matter how it splits the x, y, and z parts, this part here, the x's and y's, the length of that is at most the pumping length. So if I make it P plus 1, I can guarantee you that y is going to be some number of zeros. So it's going to consist of 1 or more zeros. So that's why I've selected W the way I did. It makes it easier for me to know what's happening in the first chunk of the first two parts of how, no matter how it gets split, how it's going to work out. Then, and since the length of W is at least the pumping length, W can be divided so that W is equal to x, y, z, where the xy part's length is at most the pumping length, and y isn't empty. So now let's use the observation that we have up here. As the length of xy is at most the pumping length, what could I say? Y consists only of zeros, right? It's only zeros. So I'm going to, just because I did this once before, I also want to show you that we could more precisely lay out what the string would look like. So I could say, I could compare how many of a certain type of symbol there are. I'm going to go about it this way, but you could abbreviate this a little bit more carefully. I'm just going to do it this way deliberately. So I'm going to let the length of y, the y part, remember I have no control of what that is, other than I know that it only consists of zeros by how I pick w. I'm going to call this L. So now we're going to consider a string that should be in the language ls. But we're going to have some fun with it. Consider string x, y to the 0, z. So remember, notice that every time I'm identifying a given string, and I'm making sure to be very clear that that is in the language by the pumping lemma, because that's one of the things we get from the pumping lemma, which is in ls by the pumping lemma. Then, now let's play around with what's going on with xz, because that's what this is. That's just xz. Then xz is equal to 0 to the p plus 1 minus L, right? Because I took away L of those symbols. Then I have 1 to the p. And since the length of y is at least 1, or L is at least 1, that means that when I compare the zeros and ones, how many there are, first, p plus 1 minus L is at least, sorry, not at least, it's at most p, right? It has to be at most p. So notice when I subtract off L, because L is the length of y, this is at least 1. It means when I subtract off it from p plus 1, it can be no more than p itself. But what does that mean then? What does that mean then? So xz does not have more zeros than ones. So xz can't be in language ls, right? Which is a contradiction. Therefore, ls is not regular. So that one's not too bad, right? But notice that the whole trickery that we had here is that we took advantage of the fact that that y part has at least one symbol in it. But we wanted to make sure we made sure we picked one in the language. But I wanted to make sure that when it cuts off a symbol, it's done in the 0 part, that it has to be a 0. So that when I cut off at least one 0, that means that there has to be, it's either going to match the number of ones or there's going to be more ones than there are zeros. Pretty nifty, right?